Hey everyone, I'm Fabio Menezes and I will talk about trajectories of coronal mass ejections, or CMEs, simulated from solar-type stars. So first of all, CMEs are products of the stellar activity which is driven by the stellar magnetic field. CMEs are plasma clouds with incorporated magnetic field ejected from the stellar corona and can alter plasma density and generates disturbances in the interplanetary magnetic field. An important aspect of CMEs is that there are significant deviations in the radial trajectories in longitude and also in latitude. They also rotate over their trajectory and therefore their magnetic field orientation is changed. This is important because when the Cme magnetic field and the planetary magnetic field have opposite directions, it can cause large changes in the planetary magnetic field. So phenomena such flares, CMEs, and stellar wind can greatly impact the space weather, which are the physical conditions of the interplanetary space. But what about other stellar systems? Well, in stars with strong magnetic activity, orbiting planets may be exposed to more extreme space weather compared to Earth. So the accurate prediction of deflection and rotation of a CME is important to know if a CME will hit the planet and impact the space weather. We simulated CMEs from the Sun, Kepler 63, and Kepler 411 using the FORCAT model, which is a model for CME deflections based on magnetic pressure gradients and the magnetic tension. FORCAT calculates the complete 3D trajectory of a CME, and for that it needs some parameters to run. Part of them are the CME parameters. The other part is about the stellar background, like the background magnetic field, which is calculated with magnetogram, which for the solar case we use a synoptic magnetogram of character rotation 2203. However, what about the magnetograms of Kepler 63 and Kepler 411? There are no magnetograms with such resolution for those stars. So supposing that these stars are similar enough to the Sun, we use the equation proposed by Adriano Valio that relates sunspot intensity and magnetic field to generate magnetograms for Kepler 63 and 411. We used the size, intensity, and position of the star spots obtained by Neto and Valio, hence determined by Origin and Valio. So this way we could reconstruct magnetograms for the Kepler stars and also calculate their background magnetic field. These are the CME input parameters. We simulate trajectories from 1.1 to 160 stellar radii with a typical CME mass. These are the CME input parameters for all simulation cases. For each star, we use 3 speed configurations and we use 3 initial latitudes based on the star spot's position on the maps. In total, 27 simulations were performed, and now I'll show you the 3D trajectories for the Kepler 63. This is just one example. So, in general, the most intense longitudinal deflections and rotations have happened up to 2 stellar radii. However, latitude deflections are more pronounced up to 6 stellar radii, and after this point they still happen but more gradually. This is due to the influence of the concentrated magnetic field regions, which cause the Cme trajectory to deflect and rotate close to the surface of the stars. In general, the total variation are small in solar simulations, intermediate in Kepler 411 simulations, and more intense for the Kepler 63 cases. Another trend in the simulations is that as the speed increases, the deflection is lower. For the initial latitudes is the opposite. And I would like to thank all these institutions, centers for the financial aid of my research, and I'll let you with some final remarks. Thank you.